In this video, I wanted to give a quick example of the main Python library for MCMC sampling. In this week's assignment, I gave you the task of finding your own mini project to test PyMC3 on. For me, I chose to look at COVID-19. I'm in a 14-day mandatory quarantine right now, and so last week I looked up the published papers that analyze the incubation time of the virus. That is, the time between getting exposed to the virus to the day when you show symptoms. I found this preprint and eventually found a GitHub repository where they stored the data they'd collected and their statistical analyses. They fit the incubation times to a log normal distribution using an R package. So we decided to redo their fitting in PyMC3 for our example today. I downloaded the data and ran the R code to pre-process it, and exported the result to a CSV file so I could get it over to Python. Over in Python, I bring in NumPy as normal, and I also bring in pandas to read in the CSV data file for me, and PyMC itself. There's a bit of setup code for plotting, and I print out some version numbers. Down here, I bring in the CSV data into a data frame and print out the first few rows to check everything is as expected. Our data is 4 numbers for each confirmed case of the virus. The first 2 numbers, EL and ER, represent the left and right endpoints for the exposure period. So our poor coronavirus victim was infected sometime between these 2 dates. The SL and SR represent the range of dates inside which the victim began to show symptoms of the virus. This kind of data is apparently called doubly interval censored. Apparently, we can, without losing too much information, simplify it a bit. So we instead say that the incubation time T has to be bigger than SL minus ER and smaller than SR minus EL. So making this transformation, we can plot the minimum and maximum values as histograms. A slightly more intuitive plot is to imagine that the incubation time is uniformly distributed between each of the endpoints, and draw an empirical PDF for T. As a first guess, let's just pretend the incubation time was observed to be exactly in the middle between the lower and upper bounds we have. If that's the case, then we can fit this observed data very easily with PyMC3. We're fitting a log normal distribution, and this has a mu parameter and a sigma parameter, which are the mean and standard deviation of the log transformed distribution. With Bayesian analysis, we think of these parameters as being random variables, and we start by creating a distribution which represents our best guess at their values. These initial guesses are called prior distributions. Since I'm not an expert in this field, I'll set up mu and sigma to be uniformly distributed over quite a wide range to reflect my lack of knowledge. PyMC3 generates distributions in a pretty intuitive way, though we also have to give each distribution a string which is the name of the random variable. I usually just reuse the variable name I've chosen. Finally, we get to the actual distribution we're using to model the observed data. We create the log normal distribution, and we set its parameters to be the mu and sigma random variables above. And we tell PyMC3 that we have observations for this distribution with the observed argument. Lastly, we tell PyMC to go and use MCMC to sample from the target distribution, which is the posterior distribution. This posterior distribution incorporates our prior distribution for the unknown parameters, but updates them to reflect the fact that we've now observed some data, and so we must have a better idea of what the parameters are. When we run this, a lot of stuff happens. By default, the nuts sampler is used. This stands for the no U-turns sampler, and it's a kind of Hamiltonian Monte Carlo algorithm, like we discussed at the end of our class one day. The nuts sampler needs to take derivatives of all the density functions in our problem, which is why the derivative calculation engine Theano was installed on your computer when you installed PyMC3. PyMC3 also ran 4 MCMC chains on my computer at the same time, from different starting values, because it could tell that I had 4 cores in my CPU. You can force it to run just one chain if this parallel code creates errors for you. The plot trace function lets us check that the MCMC algorithm didn't suffer from one of the many MCMC common pitfalls. And the plot posterior function gives us an estimate for the mu and sigma parameters of the log normal. That is, the mu parameter is between 2.7 and 2.9, and the sigma parameter is between 0.75 and 0.92. However, if we compare this with the fit reported by the original authors, we see that these numbers are quite a bit higher than their estimates of 1.62 and 0.42. So it seems this hacky approximation where we took the middle of the interval and pretended it was an observation isn't a great idea. If we try to fit the interval data directly, we have to write the likelihood code ourselves and give this to PyMC. For the intervals, we need to replace the PDF inside the likelihood product term with a difference of CDFs. Whenever we are writing math code in PyMC, the general principle is to write the code as if you were calling NumPy functions, but then replace the individual math function calls by calls to the Theano package. PyMC needs to calculate the derivatives of these functions so it can do Hamiltonian Monte Carlo, and it can't take derivatives of maths that is done using NumPy. So I dug around inside the PyMC3 code and found the logarithm of the CDF of the log normal distribution. Copying it into my notebook and doing some minor edits, I get a function which calculates the log normal CDF values I need in a way that PyMC is happy to work with. There's probably a smarter solution to this problem, and I don't expect you guys to need to resort to this level of dodginess. PyMC3 doesn't have a built-in way to handle these intervals, but it does have a generic way to add stuff to the likelihood. This is done using the potential function. Here, you add in the logarithm of the term you want to add to the log likelihood. We'll be adding a sum of logarithms of differences of CDFs. Finally, we create a new model with the same priors and add in this potential junk. We ask it to run the sampling again. I actually get the Hamiltonian Monte Carlo code giving me an error here, so for this case I tell PyMC just to use a stupid Metropolis random walk sampler instead, and that seems to work fine. And we check the trace plots and eventually look at the posterior distributions. We can see that we're now getting almost exactly the same results as the original authors in their paper. The mean parameter is between 1.5 and 1.8, and the sigma parameter is between 0.25 and 0.52.